The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
With that, we'll move along to our next presenter, which is Tim Cost from Holcim. Tim, if you'll join me here on stage, and if everyone would welcome him, please.
Thank you. Well, here's some cement guy wanting to talk about chemical admixtures. This should be good. It's true that chemical admixtures are a very important component of how we might go about developing highly sustainable concrete mixtures. And I'd just like to suggest an approach that may be useful in finding the right proportions and optimizing the performance of certain types of highly sustainable concrete mixtures. When we talk about sustainability and improving the sustainability of concrete, many times it's all about reducing the clinker content of our concrete mixtures with available technologies today. And as we do that, the reductions of the use of Portland cement through supplementary cementitious materials becomes a very important part of that. And more we're running into concrete specifications and even project owners who want to require of us higher replacement of ordinary Portland cement with supplementary low carbon footprint materials. There are a number of these very celebrated projects in recent history that make significant use of SCMs in concrete. The I-35 bridge in Minneapolis is certainly one such project with some very impressive numbers on replacement of Portland cement for high performance concrete. But unfortunately, not all projects are as conducive to the use of such mixtures. In particular, projects that may require a lot of flat work. Finishing of flat work for floors and pavements and so forth require certain aspects of performance that seem to be contradictory with the use of extended levels of supplementary cement materials. And the related performance trends that are problematic are certainly set time retardation, very slow strength gain of the mixture, and so forth. And of course, the potential of problematic performance with cracking and surface durability issues and things like that becomes more and more significant as we slow hydration rates and extend setting times. So one thing that's been found to be problematic whenever we're mandated to go to a very high level of supplementary cementitious materials is if all you do is simply increase the replacement rate of your fly ash from 25 to 50%, you're probably going to have some performance problems on your hand. So this might be a protocol that might be of interest in the next few slides here in reaching restoring acceptable performances. And these are the related challenges. As we start to use more and more chemical admixtures to accomplish certain things in our concrete mix, the complexity of this mixture becomes significant, and the predictability of those results, particularly as we change from one job to another, material-specific sources to others, we really need to be able to develop mix designs based on specific knowledge of specific material combinations. So what I'd like to suggest is the use of what we are referring to as thermal profile testing or thermal measurement testing. It's a very expedient, quick and dirty tool for preliminary performance, achieving performance attributes of interest in a concrete mixture. And this type of process is particularly suited to evaluating setting time influences, early strength and relative hydration performance, evaluating the possibility of any potential incompatibilities, as Era mentioned earlier, and these kinds of things. Now, this type of protocol is made possible through the use of very inexpensive and easily used temperature collection devices that you can buy commercially and actually apply in various types of expediently devised setups for testing. There's even getting to be some commercially available thermal profile testing devices, such as the 80 cal type field calorimeter. These are some other, this is one that Holcim is now producing in Europe that is being used internally, and a variety of other adaptations. I'll show you a few more of those as we progress. What I'd especially like to concentrate on is the use of laboratory paste mixtures. Very, very quick and easily executed process in which we actually model the paste-only content from your envisioned concrete mixture. No aggregates, just cementitious materials, mixed water, and chemical admixtures. This is a very convenient way to understand the effects of different chemical admixtures, their dosage rates, and their interaction with particular materials of interest. And the equipment used is very simple and easily acquired. It's a routine thing. What we do is pre-weigh the powdered ingredients. You see some containers, plastic containers of pre-weighed powdered ingredients. And as we're doing the mixes themselves with very simple mix equipment, we're actually batching the mixed water individually for each mix and weighing that up on the fly. And we use the medical syringes for the proportioning of chemical admixtures. This also lends itself, if you're interested in investigating the delayed admixture addition routines, you can also modify your mix protocols there. And doing this, two people can easily do 3, 4, 5 dozen mixtures in a morning. It takes us about 4.5 to 5 minutes a mix to put these up as we go. So it's very simple to do. These are the actual pieces of equipment that we use to produce the data that I'm about to show you. And by the way, we often use a curing tank preset to a particular concrete field temperature of interest for preconditioning materials and the environment, the hydrating environment, to see what things might happen at summertime temperatures in the field or even cooler temperatures associated with fall and winter. Just a quick review of what happens in a thermal profile in order to see how we use this information and apply it to concrete mix performance. This is a changing state of temperature of a hydrating mixture over the first 16 hours in this case, very typical. And the features that we're interested in, first of all, the aluminates, the calcium aluminates in cement fire off a lot of heat evolution immediately, which is then very rapidly controlled, if everything is ideal, by the interaction of calcium sulfate or gypsum in solution. And that provides us the delay period for finishing concrete and so forth. And then the main event occurs, which is, of course, the calcium silicate hydration that produces setting of concrete and ultimately the early strength of concrete. We know from experience that in this history of events, the initial setting of concrete probably occurs in this neighborhood of the timing of that sequence. As this is actually quite repeatable and has been found to be a useful tool for even estimating concrete setting times from such mixtures. A very convenient reference might be just a reference point that would be halfway up the onset of hydration from dormant temperature to peak temperature. It can be done visually or it can be done in a spreadsheet. And we use that just as a reference indicator of approximate setting time changes one mix to the next. A lot of different applications of this technology. The specific uses that I'm going to suggest in the next little bit here relate to how we can actually model a concrete mixture that is performing well and then use the same testing techniques to investigate different proportions of other materials to reproduce that performance. By the way, this is sometimes referred to as calorimetry. And just to be clear, what I'm really talking about is calorimetry would be a misnomer. Actual calorimetry is the very precise measurement of actual heat evolution from a hydrating sample. We're crudely documenting the changing temperatures of mixtures as an indication of that heat evolution. But in the truest sense, if you loosely call this semi-adiabatic calorimetry, we'll know what you're talking about. Now, here's an example of how you might use this method to give yourself an appreciation of how differences of setting time are affected by different dosages of an admixture or different admixtures. And we use these references, these 50% fraction markers for each mix, to give us an indication of the amount of setting time change that would likely result by changing those proportions. Very routinely done. Another thing that's interesting to do is to document the one-day strengths of these mixtures. In an absolute sense, the shape of this curve, while for a given set of materials it doesn't change, may actually be somewhat related to the quantity of strength produced in the evaluation period, but that's a very difficult thing to evaluate in the absolute sense. So it's also very simple just to take the same hydrating samples, whether that be paste or mortar or concrete, and do a one-day compression test on them to see what the relative strengths are. The subject of incompatibility has been suggested, and this is an excellent way to investigate and evaluate the potential for a set of materials and proportions to misbehave or abnormally hydrate. We see those things happen when the shapes of the curves change, and the one-day strength documentation is particularly useful here to help us assure that our interpretation is correct with respect to the strength generation. And this set of mixtures was exactly the same proportions and materials with the exception of admixture dose, which was incrementally changed in an aggressive mixture at summertime concrete temperatures. And you can see in the case of the normal hydration, the green curve there, the strength produced at one day, all the way to the most extreme case for the most incompatible set of conditions, which produced virtually no measurable strength in one day and would have been a very unusual setting time trend. These incompatibility occurrences are driven by a variety of things, but principally certain SCMs. Again, if we're developing sustainable mix, this is of particular interest, particularly Class C fly ash that may contain significant aluminates. Certain admixtures, almost all admixtures, have some bearing depending on the dosage rate. Certain admixtures more so than others. And as we get into multiple admixtures, these questions become infinitely complex. Hot weather is another incompatibility influence because the solubility of calcium sulfate changes in an unexpected way. As temperatures get warmer, solubility actually becomes more difficult for calcium sulfate in solution. And finally, there may even be cements that the adequacy of the sulfate or the gypsum content, at least in the soluble forms, might be in question for very aggressive concrete mixtures. So different combinations of these things can become particularly challenging. How we would go about using this technique to develop a highly sustainable concrete mixture, there's a variety of different approaches that could be used. I'm just going to show you an example of what you might do with some commonly available materials. And what we're really trying to do is to replicate the early performance, particularly setting time and early strength development of traditional concrete mixtures that do behave adequately for performance in flat work finishing. And what we're actually going to do here is take those proportions from commonly used concrete mixtures and put those materials together to establish baselines for our subsequent testing with varied proportions in materials in a more sustainable type mix design. And we'll do this through initially increasing the SCM level, and then we might actually need some additional admixtures in order to reduce the water cementitious ratio for early strength development. Side effects from that may be additional retardation that needs to be compensated for with accelerating admixtures and so forth. So here's how that goes. First of all, just the selection of materials. There are a lot of things that can be done with this very simple testing if you have certain options for materials. And a baseline mix design to model for your initial material selection process might be one that you've had experience with. That would be particularly challenging for a set of materials to survive. Or you might just come up with your own set of proportions that are very complex. That would be what we kind of think of as a high sulfate demand mixture. Here's 7 different cements are compared in an otherwise identical mixture. And you see the difference in the onset of hydration that results in different setting times for that combination. And in one case, we actually have a cement that completely failed the test and produced essentially no measurable one-day strength. So if you have different cements to choose from, it might behoove you to pick sample A or sample E as the faster setting cements in this combination of materials that you might be dealing with. Just an example. You could certainly do the same thing for your chemical admixtures. These are some comparisons of different admixtures selected for dosage rate based on about the same level of water reduction that you could accomplish. And it's no surprise that the common type AD products have a lot of associated retardation. Not a good selection for highly sustainable mixtures in most cases because retardation becomes one of our problems. But even the polycarboxylates and mid-range type products have some variability in set time influences, and to select one with the minimum amount of retardation that's associated with it is probably something that we want to do. Now, in the choice, the selection of, and the tolerance for the level of replacement rate of the particular SCM materials, this is an ideal type of test to get a really good feel for what the performance trends of these materials is going to be and where the sensitivity might be for maximum practical level of replacement rate given your other materials and proportions. Here we've taken 3 different representative SCMs, a slag cement, a Class C fly ash, and a Class F fly ash, and compared them at various replacement rates in these paste mixtures in the laboratory. Very simple process. All these were done in virtually a couple of hours. Let's start with looking at the F ash. This is a very low calcium, pure pozzolan Class F fly ash. And as you go from no replacement at all in the case of the green curve to up to 40% down here, what's really happening is pretty much just dilution of the OPC in the performance that's associated with that. You can see the equivalent effects on one-day strength. Very little potential incompatibility of material influences from this particular source of Class F fly ash. The slag cement down here on the bottom, slag cement's up to 50% or so common in concrete. It's really not much of a challenge most of the time. And even with aggressive temperatures and admixtures used in these combinations, by the time you get to 50% replacement, there's some things that are changing the shape of the curve a little bit. You really have to go beyond that so you get into real problem zones with that material. But the Class C fly ash is a little bit of a different animal. And in this aggressive mixture, the Class C fly ash replacement rates much beyond, say, 15–20% are beginning to show up as distorted in the hydration profile history. And by the time you get to 30 and 35%, notice the one-day strengths, those materials are clearly experiencing what we refer to as incompatibility materials caused by insufficient sulfates available in solution. That being the case, as we explore mixed development, we might expect to see problems out of this material. Now here's how we would go about using this technique or this approach to actually model successful mixtures and reproduce their performance in highly sustainable mixtures. These are 3 different mix designs from common concrete in the marketplace that have been modeled in paste in the laboratory. And they are the same 3 materials that we've just investigated: a slag cement at about 30% replacement, an F-ash at 15%, and a C-ash at 15%. And we're establishing thermal profiles that will allow us to establish a target band, if you will, this shaded band that will give us a reference for future use in the development of a concrete mix design that will perform in a roughly equivalent fashion. Also, the one-day strengths, we can do the same thing and come up with somewhat arbitrary, but at least a minimum strength requirement target for our one-day paste mixtures going forward. I should point out that these were modeled from concrete mix designs that actually used a couple of different chemical admixtures, and the AD type admixture is one that we know is not generally preferred for highly sustainable mixtures with high cement replacement, so we'll have to deal with that going forward. It's interesting as a next step to see just what might happen if we do nothing but go up from the 15 or 30% cement replacement to a 50% cement replacement. If our specifications are calling for a concrete mix that has only 50% ordinary Portland cement content, then this would be an interesting next step. And of course, we see some mixtures with some retardation effects. We see much lower one-day strengths. We're going to have to adjust the mix proportions to account for those things. Something that's, I mentioned that the Class F fly ash mix with the lignosulfonate water reducer, the retardation from that has put that mix not on an even keel for competing with the others. So let's throw in a 4th mix that uses the same polycarboxylate as the other mixtures, and you see that the setting time effects are actually back into the target band for now, both for the F-ash and the slag cement. But the C-ash mix has a problem set time. So we're going to need to address those things. But first, let's try to get our one-day strengths back in target. And to do that, we're going to need to lower water cementitious ratio. Chemical admixtures are obviously the tool that we need for doing that. So if we increase the dosage rate of the chemical admixtures and lower the water cementitious ratio, in this case generally from 0.4 down to about 0.32, then now we have a set of one-day strengths that are beginning to bump our target band. Okay, we'll actually improve those a little further with the use of some accelerators later on. But this, for argument purposes, this gets us in the zone. Kind of interesting too that the slag cement mixture at 50%, you know, we're familiar with that. It's not even struggling yet. So just for giggles, we threw in a 60% slag cement mixture here just to see where we were. And we're still at an interesting set time comparison relative to the F-ash and C-ash. So just for an point of interest. Unfortunately, the chemical admixture use in this case has now retarded our mixture to a point that the setting times are no longer, any of them, in the target band. So we're going to need to accelerate this mixture for adequate performance in flat work finishing. We do that with accelerating chemical admixtures. We're going to do it with non-chloride accelerating admixtures in this case. And again, we try different things. We vary the proportion of that non-chloride accelerator in replicate mixes to see where we need to be. For the F-ash mixtures, a pretty mild dosage rate, something on the order, this product I think ranges up to about 40 if you language you speak in dosage rate. This would be about 10 and about 20 ounces per hundredweight. It doesn't take too much to get us in the target band. And again, this improves our one-day strengths. The slag cement mix at 50% is already close to the target band, so it takes very little, even less than probably 10 ounces per hundredweight of that chemical admixture. Again, the one-day strengths are improved. But the C-ash is a problem child. At 50%, even a maximum dose of this non-chloride accelerator doesn't quite get us in the band for target set times, and now we see some incompatibility occurring, or we suspect that's what's occurring. to support that, our one-day strengths are not improving as we go to higher dosages of the chemical admixture accelerator. And to confirm this, if you're interested in doing this, very simple, just to reproduce one of those mixtures with incrementally higher doses of a separate calcium sulfate addition. This can be ground source gypsum, it can be laboratory grade Terra Alba gypsum, or even plaster of Paris from your local hardware store. And sure enough, as you increase the SO3 level of the resulting SO3 level of the mixture, we restore normal shapes. We show much improved one-day strengths, confirming that we had an incompatibility sulfate balance problem. Now, you can't do this in concrete. You don't want to try that. So what we've got is a situation where we can now rule out the Class C fly ash if we need to go to a 50% replacement level in this mixture. You might be able to use 40%. You'd have to start over and try that again. The final thing to do in the sequence of events is to check and see if you're still going to be okay at your highest envisioned field temperatures in concrete. So we've bumped our mix and cure temperatures up to, in this case, about 96 degrees Fahrenheit. We've reinvestigated the F-ash and the slag mixes. Of course, are actually setting faster now. We could even reduce the non-chloride accelerator dosage. The one-day strengths are now ample. So this is just a process suggestion, but you see how simple this is to do many different replications of combinations that will be necessary to investigate in your process. And just to show you kind of the example of why it's important to model the temperatures of the range temps you would expect to see in concrete field. Here's 4 different mixtures, different sets of materials, different admixtures, which at laboratory temperatures, they all, one straight cement, one 25% C ash, one with the ash plus a nominal dose of a lignosulfonate, and then with an extreme dose or a high-range, high-end dose of a lignosulfonate. And all of these are still performing normally, one-day strengths at laboratory temperatures, but at 93 degrees Fahrenheit, the mixture with the highest dosage of admixture is now in complete incompatible behavior. So temperature alone can drive whether or not this is a problematic occurrence. So in summary, this is just a suggested example of how you might, through this process, define some materials that work and some proportions that probably replicate acceptable early performance in your mix design. It's now time to take this mixture to the field or to the laboratory and put up actual concrete to verify your preliminary proportions. You might have to do some additional fine-tuning of the mix for finishability, for bleed water effects, whatever it might be. But now you have a general guideline for what the limits are of the materials and proportions to get into this very sustainable mix design realm. And the same techniques are very useful in remedying any potentially problematic behavior that you might encounter on the job by taking the materials back to the laboratory and doing a quick investigation. So with that, I would be glad to try to address any question.
Thank you very much. Very interesting. My name is several. And my question is on the curing temperatures you use, HRWR. Because it's an insulated box, how did you get your curing temperatures? You put the box in a hot room?
Thank you. Very good question. The device that we use, and this would be best accomplished with a more sophisticated laboratory curing cabinet that you could set at material at temperatures, curing temperatures of interest. We're using, for simplicity, a programmable curing tank, the same type of tank that you might use on a job site or in a construction trailer for curing concrete cylinders, where you can actually set the temperature on the curing tank all the way from, I think this tank goes from somewhere in the neighborhood of 40 degrees Fahrenheit up to maybe 140 degrees Fahrenheit. And it's got a water bath in the bottom and then a table above the water bath, which is the environment of interest for the curing samples. Now, we actually also precondition the materials prior to mixing to that same temperature to simplify data evaluation, but we use that curing tank. It's not perfect in that there's a little bit of temperature fluctuation, but you can get very, very close to what you're after with that simple piece of equipment.
Thank you, Tim. Thank you.